Hello, this is Joshua, and before we proceed to the next lecture, let's answer first the given exercises from the previous lecture. So if you haven't answered them yet, okay, kindly skip through the following slides muna. Okay, so for question number one, okay, the amino and carboxyl groups of amino acids are bonded to which carbon? Okay, so before we answer this, focus your attention on this figure. Okay, so just to review, in your organic nomenclature, remember that for compounds containing carbonyl groups, okay, uh, Greek letters are used to describe the proximity of each carbon atom to the carbonyl group. So by the way, note that the carbonyl group itself does not receive a Greek letter. Okay, so you denote alpha, okay, the Greek letter for A, to the first carbon attached to the carbonyl group or attached to the carbonyl. And the system continues naming in the alphabetical order with Greek letters as shown. Okay, so just an extra point, you can also apply this to the hydrogen atoms attached to the carbon atoms. Okay, so for example, hydrogen atoms attached to a beta carbon is denoted as beta hydrogens. Now let's apply that in amino acids. Remember, sabi natin, the first carbon adjacent to your carbonyl group is denoted as your alpha carbon. And we can see that both your carbonyl and amino groups are bonded to the, okay, we can see that both amino group and carbonyl groups are bonded to the alpha carbon. So the answer here is letter A. There. Okay, so moving to question number 2, okay, the side chain groups of amino acids are bonded to which carbon? Okay, so if you will also apply our knowledge from earlier here, we can say that the R group is also bonded to the alpha carbon. So the answer here is letter A as well. Okay, so for question number 3, the amino acid which occur in proteins. Okay, so remember, we mentioned that when it comes to proteins, the building blocks here are your L-amino acids. Okay, how can we remember this easily? We can just think that L stands for life. Okay, so some trivia here. No one really knows why the L configuration of amino acids are the preferred building blocks of proteins. But one thing is for sure, no, it's via evolution. There are actually different theories with regards the prevalence of L-amino acids in biological system. Okay, so one of the theory here is that one of the theories here is that it's accidental or by chance. Okay, so by chance, the initial mixture of enantiomers contained an excess of the L configuration. Remember here your enantiomeric excess from OrgChem. Okay, so some groups argued that racemic amino acids were formed by chemical evolution in the hot prebiotic C, now which gradually cooled down. And as a result of cooling down, okay, the solubility of the C decreased. Okay, in which case, incidentally, one of the D amino acids, suppose for example, the asparagine, crystallized, no, at first, followed by the crystallization of other D amino acid on the crystal of that D asparagine, no, leaving the C L-rich. And then, from the L-rich C, cell develop. Okay, so another theory proposes that an extraterrestrial substance generated L-amino acids. Now, so apparently, okay, the left-handed radiation, for example, okay, from a rotating neutron star could lead to left-handed amino acids in space. Now, which would explain the left-handed amino acids found in meteorites. Now, so this concept resembles the idea that the cell came from the extraterrestrial space. Now, so by the way, okay, the answer here is A. Okay, so for number 4, okay, so the question is, what is the charge on the tetrapeptide given at pH 7? Okay, now so to answer this, you have to check the form of each amino acid in the peptide bond, no, in the given pH. So by the way, you also have to check here the pKa values of the amino acids present. Okay, so remember, we said that, okay, when your pKa is less than that of the pH, you have it's basic, no? So thus, it's protonated. While if pKa is greater than that of the pH, it's acidic, no? So thus, it's protonated. Okay, so shown on this table, okay, are the pKa values of the different R groups, no, in your amino acids. Okay, na so for lysine, okay, pKa for the carboxyl group is 2.18, which is less than the given pH, meaning it's deprotonated. So you have a negative charge here. The pKa naman for the amino and R groups are 8.95 and 10.53 respectively, no, which is greater than the given pH. Thus, you have a positive charge for both of them. Okay. So in total, you have a positive 1 charge for your lysine here. So there. Okay, so let's focus naman with glutamic acid first. Okay, so the pKa of both, okay, the carboxyl and the R groups are less than the given pH. So you have here a deprotonated form. So that would mean that, okay, they would bear a negative charge. And then, okay, for the amino group, since the pKa is greater than the given pH, it would bear a positive charge. So in total, okay, you will have here a negative charge. So there, negative 1. No, so for histidine naman, no, so the common mistake here would be to do what we did on the previous amino acids, no? And by doing so, okay, so you would arrive on a total charge of negative 1, which is wrong. Remember, okay, we mentioned in the previous video that histidine has an almost neutral pI, which is around 7. And as a consequence of that, no, and since we have a pH around 7, okay, so the total charge of histidine would be equal to 0. So there. Now we have the specific charges, no, of each amino acid present. Okay, so now that we have the charge of each amino acid, okay, to get the total charge of the tetrapeptide, okay, you simply have to what do you call this, to get the summation, okay, of the charge of each amino acids. Now, so you have here positive 2 for both of your lysine, okay, so 0 for histidine, and then negative 1 naman for glutamic acid. No? So in total, okay, you have a positive 1 charge for your tetrapeptide. No? So the answer here is letter B. So there. Okay, so for question number 5, okay, you were asked here to arrange the pI of the given amino acids from lowest to highest. Okay, so before anything else, let's evaluate the properties of the given amino acid in terms of their R groups. Okay, so aspartic acid, okay, is an acidic amino acid, hence the name. No? So asparagine, on the other hand, has a polar uncharged R group. And lastly, your arginine, okay, your arginine here is a basic amino acid. Okay, so there. Shown on this table, okay, are the pKa's or pKa values of the given amino acids. Okay. So, we'll be filling the blank column for pI. Again, the formula for pI is this. Okay. Remember on our previous video, we provided a technique in calculating for the pI. So if you have an acidic amino acid like aspartic acid in the given example or in the given question, okay, to calculate for the pI, you just have to use, okay, the lowest pKa values. Now, as can be seen in the table, Okay, the two lowest pKa values are for that of the carboxyl and R groups. Okay, so invoking the formula, you will have here a Pi of 2.77. On the other hand, okay, for your basic amino acid, like your arginine here, okay, to calculate for the Pi, you have to use the two highest pKa values. Again, from the table, we can see that these are the pKa's that we will be using. So we have a Pi of okay, 10.76. There. Bakit pala ganito yung technique? Remember in Anachem and Organic, okay, Orgchem, sabi doon, if you have a low pKa value, you have an acidic species. So that's why the two lowest pKa values are used in calculating the Pi of an acidic amino acid. And when you have naman high pKa value, you have a basic species. So the two highest pKa values are being used in calculating the Pi of a basic amino acid. Now, so lastly, for asparagine, okay, we said that it has a polar uncharged R groups. And you can see in the table that you don't have pKa value for the R group kasi nga uncharged siya. Okay, so you don't have a choice but to use the available pKa values. So the Pi here is 5.41 after invoking the formula. Okay, so we're not done yet. We still have to arrange it from lowest to highest. Okay, so aspartic acid comes first, followed by asparagine and by arginine. Now, in terms of their one-letter code, okay, we have this sequence. Now, so you have your D, N, and R. So the answer here is letter A. There. Okay, so for question number 6, no, so the peptide bond daw is what? Now, so let's evaluate each of the choices. Okay, so letter A says that the peptide bond is formed by elimination of water, okay, between two amino groups of an amino acid. Okay, this is wrong because, okay, you need the carboxyl group of the other amino acid. Recall that it's the condensation of an alpha amino group in one amino acid and an alpha carbonyl group or alpha carboxyl group of another amino acid. No, so letter B naman, so wrong yan, no? So letter B naman says that peptide bond has acidic and basic characteristic. This is wrong as well because it's your amino acid that has amphoteric property, no, not the peptide bond. Okay, so ibig sabihin, okay, letter D is also wrong. Okay, which leaves us, okay, with letter C as the correct answer. Your peptide bond, okay, has a trans and planar configuration. Planar due to the hybridization of the carboxyl group and amide group, which undergo, okay, very little rotation around the amide bond. So there. Okay, so moving on to the next topic, okay, and this video will be discussing about the three-dimensional structure of proteins. So as usual, we have on the next slide the topic outline for this lecture. Okay. Okay. So these are the topics that we will be talking about later. So just read them. Okay, so there are many available conformation for proteins, okay, or your three-dimensional structure. Why? It has to do with the flexibility of the amino acids linked in your peptide bond. Later, we'll discuss those. Okay, so of these many possible structure, at least one major conformation has a biological activity and hence is considered the protein's native conformation. Let us note that many proteins have no obvious regular repeating structure. And thus, these proteins are frequently described as having large segments of random structure. Okay, as shown in this figure, okay, you have here a very, kumbaga magulong structure. Okay, by the way, so you have your A random structure nga, diba? So, by the way, we can also refer to your native conformation as your natural structure. Now, we said that the native conformation of your protein is the one that has biological activity. Now, what do you call naman your protein that lost its biological activity? Say, for example, upon application of heat or large change in pH. Remember, we mentioned on the previous lectures that pH is one of the factors that affect the effectivity or the activity of your enzyme, no, which is a protein, by the way, no. So you call that your denatured conformation. Okay, so again, by the way, yung mga binanggit ko kaninang factors are your denaturating agents, no, which we will be discussing further as we go along. Now I have a question. Although it's a bit okay, so I have a question, no, although it's a bit early for the discussion. When your protein is denatured, does it automatically mean that it's already useless? Okay, the short answer here is no. We'll be expounding on this answer later because to be able to do that, we need first to understand the different levels of your protein structure, no? Which we'll be discussing, okay, on the next slides. No? So, we'll be answering these later. Okay, so what are the levels of protein structure? We actually have 4 levels, okay, now which are listed here. You can just go through this and we'll be discussing this one by one on the following slides. Okay, so the first level of protein structure is the primary structure. Remember here that the primary structure of your proteins pertains to the sequence of amino acids in a polypeptide chain. Okay, and again, it's read from the N-terminal end to the C-terminal end of your peptide chain. Let us note, okay, that the primary sequence of proteins ultimately determines its three-dimensional structure, which in turn determines its properties. Okay, so let's have a representation. The peptide capes, okay, recall that the N-terminal amino acid is listed first, no, NCC, is different from the peptide space. Okay, it's different from the peptide space, even though they have the same number and kinds of amino acids rather. And why is that? Because they have different amino acid sequence. Magkaiba yung pagkakasunod-sunod nila. And therefore, we can deduce that both peptides would have different properties. So, would probably exhibit different functions. Note that the order or sequence of amino acids can be written in one line because the primary structure is the one-dimensional first step, okay, in specifying the three-dimensional structure of your protein. So, pwede mo siyang isulat ng isang linya lang, kagaya ng ginawa ko dito. Okay, so we've been talking about the primary structure of your protein since earlier, no? So what is its importance nga ba? Okay, remember, we mentioned that the primary structure or the amino acid sequence would determine the three-dimensional structure of your proteins and consequently, okay, its properties. Now, even just small changes, okay, in one amino acid in the sequence can actually alter the biological function of that specific protein. Example here is your hemoglobin in sickle cell anemia. Now, so in this genetic disease, okay, red blood cells or RBCs cannot bind oxygen efficiently. And your RBCs also assume a characteristic sickle shape, no, as shown on the figure. Okay, giving the disease its name. Okay, now what's the consequence of this shape? Okay, the sickled cell tend to become trapped in small blood vessels, which cuts off blood circulation, and causing organ damage. So can you imagine that this drastic consequence was cause of a change in one amino acid residue in the primary sequence. No? So your glutamic acid was changed into valine. See, from an acidic and charged R group amino acid, okay, to an aliphatic amino acid with an uncharged R group. No? So probably naapektuhan nito yung electrostatic attractions ng structure mo. Okay, so however, okay, it is important to note that the result of such amino acid substitution, okay, range from negligible effects to complete loss of activity. Now, depending on the protein, okay, and the nature of the altered residue. Now, let's move to the secondary structure of your proteins. Okay, so the secondary structure of your proteins, sometimes referred to as the local shape, is the hydrogen bonded arrangement, okay, of the peptide backbone. Okay, note or of the peptide chain. Now, note that the nature of the bonds in the peptide backbone plays an important role here, and that the stabilizing forces, okay, only comes from the peptide backbone, no, which is your hydrogen bond. Okay, the conformation of protein backbone, or of the protein backbone, is influenced by the Ramachandran angle. You have your phi and psi. Okay, your phi here designates the angle of rotation, okay, between the alpha carbon and N, while your psi naman designates the angle of rotation, okay, between the alpha carbon and C. Okay, so how do we remember daw if it's phi or psi? It's like this daw. I learned this from Review Center. Since psi daw is K-pop Korea from Korea with C, no, Korea. Ibig sabihin daw, it's the rotation around CC. So, sa phi, kayo na bahalang mag-isip. Okay. There are two kinds of secondary structure that occur frequently in proteins. Your alpha helix, okay, and beta pleated sheets. We'll discuss both of them as we go along now. So by the way, both of these structures are stabilized, okay, by hydrogen bonding. Note that these two are not the only possible secondary structures, but they are by far the most important and deserve a closer look. So shown here is an example of alpha helix. Okay, so note that the usual alpha helix is right-handed, meaning, okay, the coiling of the helix is clockwise. Okay, that is if your point of reference is on the top view. It is stabilized, okay, by the hydrogen bonds, okay, parallel to the helix axis within the backbone of a single polypeptide chain. No? So what does that mean? It means that from the N-terminal end, C double bond O, or the carbonyl of each amino residue, is H bonded to the NH group of the amino acid 4 residues away from it. No? So, okay. So, you may want to count it. No? So, okay, so there are 3.6 amino acid residues per turn. Okay. Pitch here corresponds to the linear distance between corresponding points on successive turns. Okay, and all R groups, okay, point outward, okay, from the helix because there is not enough room for them to in the interior. Okay, so there. Okay. Let's discuss naman about the factors that disrupt alpha helix. First, we have here proline. Why? For two reasons, no? First, because it creates a bend. Remember, we said before that proline is rigid due to its cyclic structure, meaning you have a restricted rotation. Second is that its alpha amino group cannot participate in the intrachain hydrogen bonding. So there, you have proline. Okay. Second naman, we have, okay, second naman, we have strong electrostatic repulsion. No? So this is due to the proximity of several charge R groups, no, of the same sign. Remember that, okay, same charge repel. Now that repulsion in the R groups of the same charge amino acid can actually disrupt your alpha helix structure. Let's have an example. Look at this portion of amino acid sequence, okay, in a polypeptide chain. And say you were asked if it can form an alpha helix structure. First, you check here the nature and property of the individual amino acids. And upon looking, you notice, okay, that it has two successive negatively charged amino acids. Okay, okay, so you have your D and E amino acids. Also, you notice that proline, okay, is also present. So there, we can therefore deduce that it can't have or it cannot have an alpha helix structure because of the presence of these disrupting factors. Now lastly, steric crowding is also a disrupting factor. Why? Eh pagtabihin mo ba naman ng dalawang bulky groups, no? So you'll have here a steric repulsion due to the proximity of several bulky R groups. So there.